Everyone, we're going to take a closer look at this board here, in particular the G25 processor here that does pretty much all of the graphics processing on this board. We got a few things hooked up here to capture signals. So logic analyzer sitting over here with 3 signals hooked now. We're going to hook up a bunch more in a few seconds. We have the pixel clock, well, not really the pixel clock, but it's a 13 megahertz clock that the pixel clock is derived from. Right here we have the ready signal on the CPU, which is used to manage access to memory that's shared between the CPU and other resources. And over here we have a convenient point to grab the video sync signal, so we can get an idea of where in the frame we are with when we capture signals. What we want to do, what we're trying to work out today is like, how does this, the G25 access memory, and how is that memory access shared with the processor? So right over here is our 2 VRAM chips, which is the video memory for this entire board. It contains the tile map data, information about offsets and row scrolling, and it also contains all of the sprite information. So where sprites are on the screen, which sprites to draw, et cetera, et cetera. The CPU writes to this memory via the GA25. So CPU writes to certain addresses, those go through the GA25, and it manages how the CPU accesses this memory. While drawing the frame, the GA25 reads the information from this RAM and also reads the pixel data, the image data from these ROMs right here, which contain both the tile maps and the sprite image data. And from that, it generates the video data that actually gets output and sent to these 2 RAM chips here, which contain palette data, and ultimately out through a DAC and out to generate color video signal. So what we want to do today is monitor one of these RAM chips to see which addresses are accessed when, so we can get an idea of what the timing might look like for the GA25, because it needs to read, like I said, the tile map data and the sprite data all at once, and it needs to manage accesses that might be coming from the CPU into the GA25. We have this very useful, but also kind of unwieldy clip, which is hooked up with all signals to the address lines. Let me show you what this chip looks like. So this is the data sheet for this RAM chip, and we can see we have a bunch of address signals right here. These I/O signals are the data signals, and then we have some more address signals and some other control signals here, the chip select, the output enable, and the write enable. So what we've done on this clip right here is put signals on all of the address lines and all the control signals. We've ignored the data signals because we don't care about them too much, at least for this analysis. So I'm going to turn the board off, and I'm going to clip this thing onto one of these RAM chips and try to do it in a way that doesn't mess up a bunch of existing stuff that we've hooked up here. So hopefully we can get this on here correctly and nothing else pops off the board. Sorry, you can really see what I was doing, but there. So now this is sitting on top of one of these RAM chips. We don't need to monitor both because they both get the exact same addresses. The only difference is what data is returned back, which, like I said, we don't care about all that much. We only have 1 ground on this chip, so we might get a little bit of a noise in the signal because we don't have good ground returns, but let's see what we do. So let's power the board back on and see if something terrible happens. And no, okay. So it's still working. We haven't shorted anything out and caused any issues. Let's see. So if we go to DSView here, which is the logic analyzer software. So I have set up, enabled all the signals we need, and I've named all these based on where they're mapped to on the thing. So we've all of the address lines, and then right down here we have those the clock signal, the 13 megahertz clock signal, the sync signal from the video, and the ready signal from the CPU. We're going to not pay too much attention to these right now, but let's just capture without any triggers and see what we get. So a lot of stuff. Let's zoom out a little bit and see if we can get our bearings. Okay, so this is a 50 milliseconds, so we should have about 3 frames here, which would be like 40 something milliseconds. You can see if we zoom in on the sync signals here, these longer syncs are the vertical blanks, the vertical syncs, and these shorter syncs here are the horizontal syncs. So if we counted these up, we would see how many lines we have in each display. But we can, mark this as the end and the start of a frame. All of these address signals are here. They're like, very difficult to interpret what's going on. So what I use for this, let me hide the overlays. What I use is a decoder to just decode these values into something that's readable. Let me enable that. I've set it up with all the address lines as being the parallel data lines. Haven't set a value for D0 because everything here is accessed on even addresses. And I want the address values, the hex values that I see here to match what you would see in MAME or in my test ROM, so they're not shifted by 1 bit. So let's do that. Now this lineup here will update with the real address values we're getting. Each of these things, we got to zoom in because there are a lot of them. Okay, so now we see what addresses are being accessed at each point in time on the CPU. If we look down at the, let's move these signals so they're in a convenient location because these ones are important. We have the chip select, the output enable, and the write enable. These are all negative signals, so these will go low, like this will go low when we're actually writing. These will be low when we are reading from the chip, which is probably pretty much all the time. So let's find the start of a frame again. Let's zoom in right there and let's see what addresses we're reading. Right here at the start. This is where the sync signal basically goes high again after a long time being low, which marks the start of a new frame. And in here, I can see like we're reading from EE06, EE08. I know that the sprite data in the on the CPU is, if we go to this object file, so sprite data here begins at EE00. So that is right here is reading sprite information. Let's find where we read EE00 because that's going to be the very start of the frame. So EE00 right here. So this is starting. We should see this pattern every line. Like if we go to the start of another line, let's mark it and zoom in on this one. We should see again, we're restarting, reading the sprite data, every single line, starting at EE00. And where are we going to? Let's see what the maximum sprite thing it reads, which should be we should see EF3C. So that is the last sprite we read each line. So from this we could determine what is the how many sprites are we getting in a single line. So we're reading all the way to EF3C minus E00, 316 bytes. If each sprite is 6 bytes, so let's divide that. We probably need to change this to E is the real value, so 53. So, thanks, right. So yeah, we're getting through 53 sprites on each line, which is probably the limit of what the hardware can support. So let's zoom out. So I saw another value there that was interesting. The two other values that we are in kind of special locations. So 0 to basically the end, like 0 to F000 in the VRAM is all of the tile map data. And then F000, no, yeah, F000 is where there's, is it row offsets or, let's see what we have, because we use them here. So F000 is where we have some, which is the row offsets, which are like X offsets. So I think that is the row scroll that you see here. And then the Y offsets is what controls this, this kind of row offset stuff, which kind of allows you to change the line that each line on screen is addressing in the tile map. So I can, like here, it's kind of stretching out that data by doubling up the lines that are reading. And in the row scroll, it means you can individually scroll each line of data. So that's these two values here are at F000 and F800. And if we look in here, we should see at the start of each line, it's going to be reading those values somewhere, or values in that range at least. Okay, so what we see here is we have right here. So here, I think, is where we can kind of consider the very start of a line of data. So we're reading some X or Y offset values from for one of the layers. Then we read some sprite data here. Then we read another set of offset values. Maybe for a different layer, we read some additional sprite data. And then right here is another set of offset data right in this area. And then more sprite data. And this is more offset data. And another sprite. And then it looks like right here we start reading tile map data. So we read each tile map is each like tile on screen is two 16-bit values. So one tells us which what the actual tile is, and the rest is kind of attribute data. So here we have BFF6, which is probably is the tile data, and then the rest below that, which is the attribute data, I think gets read in. So here we have reading kind of our first piece of tile data from VRAM, and it's interleaved with more sprite reads. So we have an additional 2 sprite reads here. We have another tile VRAM read here. This is probably the other layer. We do an additional sprite read. These 2 values here are weird. It doesn't look like this is anything. This might just be kind of garbage data as it transitions from reading a sprites, and sprites are kind of 3 reads, 6 bytes, 3 words. So it doesn't really divide evenly by 4. But we would need to look and see if there's some pattern in this data. But it seems like we read 2 words of tile map data, 2 words of sprite data, 2 words of tile map data for probably the next layer, 2 words of sprite data, or 1 word of sprite data to finish this parallel sprite, and then potentially just garbage reads that don't do anything. And then we move on to the next tile. So this is, if we count up how many clocks this is for, this is 4, 8, 12, 16, so 16 clocks. And every 2 clocks is 1 pixel clock. So there we have 8, basically like 8 pixels of what's going to be on screen. We managed to read in 2 tiles and a sprite. And then this is going to repeat for really the rest of the line, slowly increasing this up. So like, again, right at the start of the line, we read in, like the first reads from the start of the line are this kind of let's call it metadata that exists for each row, where we read the X and Y offsets for each layer. We start reading sprites right at that point in time too. And then we, keep going through, and then it's just going to continue looping through for each tile map and each sprite on the line until it finishes the line, and it's going to reset and kind of do the same thing again for the very next line. Let's clear all of these markers. Let's keep them. So it gives a pretty good idea of what the actual timing is for like each row of data. We would, we see even if like row scroll and row offset are not enabled for every line, but we still read that data. It's just how that data is used to calculate what the actual offset into the tile map is going to depend on whether these like row scroll flags are set for a layer. Now, we only set it for layer 0 here in the test code, but it's going to get read for layer 1 and layer 0 regardless. The other thing I wanted to look at real quick is how this ready flag gets used. So the ready flag on the V30, when that goes low, it basically, it's an input into the CPU. And when it goes low, it stalls the CPU on any read it's doing. So when the CPU requests a write, and we see these are writes here because it is, this write flag is going low at some point. So right here, the CPU requested a write. Oh, now I actually know. Okay, this will be interesting. So the CPU is requesting a write right here. I can, without zooming in, I'm going to guess that this ready flag stays low until we have either once or twice we've gone through the loop of reading 2 words of tile data, 2 words of sprite data, 2 more words of tile data, and then that 1 word of sprite data, and then there was that garbage kind of slot at the end of that sprite data. That spot right there is a spot that's going to be filled by a CPU read or write. So we will see it basically holding the ready flag until it gets to that point in the cycle where it can, where nothing else is accessing the memory, and we can give that memory access to the CPU. So there's 2 write enables here. So I think what we saw something similar on the M92 and the M107, where it was taking kind of doing 2 cycles for most of these to get through. I think it depends on what exact time the CPU read lands at. So let's mark where the write enable is set. Let's mark where it's set again. Let's mark the beginning and end of this time slice. And if we zoom in right at the start, so this start point is kind of going to be arbitrary because this is the CPU requesting a write, and then the GA25 is saying, wait. It's basically saying, you can't write to memory yet, so just wait because I'm in the middle of reading from memory myself. So we will see we have, we're reading some tile data here. We are reading some sprite data. We have 2 full words of sprite data being read here, so it's not the cycle that does the kind of garbage read at the end. We then read an additional set of tile data, and then here we read the 3rd word of sprite data, and then there is this write enable is set here is the point at which we are writing. So it looks like we're writing into the sprite buffer at this point in time. So it's here where write enable gets set, output enable gets disabled, and now we're that kind of like garbage, like unused address was existing before, is now where we're actually setting the write address. I think it might be clearer if we go to one that's doing, and this will, I'm pretty sure this will write to the exact same address again. Yeah, it's still writing to E04. So it's, I don't quite know why it does those double writes, because here we're just doing a single write. I think it just depends on just the exact spot in the cycle we end up. So this is going to be more sprite writes here. And then hopefully we'll get to some tile map writes. Probably not here, but Yeah, we're still writing to, so here we're writing to E14. Just zoom out. We can, if we look at the patterns, we'll see like, oh, these are like some sprites, and then if we go over here, it's almost certainly some text or something in the, during the v-blank. So again, the ready here is where the CPU is requesting a write. The write enable doesn't get set yet until we hit that cycle where we have a free spot in the loop. So here we go again. So we're reading 2 words of sprite data, 2 words of tile data, the final word of sprite data, and then this spot right here is where we're writing into VRAM. So this is like writing one of the scroll offsets, probably. Like that would be like some code in here. So we're writing into those offset buffers. And it will, the write itself happens when we hit that point in the cycle where there's a free slot to actually read or write from memory. Why it does 2, I don't know. It doesn't always do 2. You'll see here it's writing the same data in the same slot, and then probably just based on exactly when we hit that interval, right here we have a single one. But it is the same pattern. So it's likely just something in the state machine is deciding that it doesn't, that it's going to go for another loop. Tile read, sprite read. It looks like we've hit the write just as we are about to, just as we've entered this kind of this free spot right here after the 1 word sprite read. So we will catch it again like immediately as it goes around. That's probably why it's not doing 2 in this case. But if we zoom in here, we will see that we are again on the single sprite read from EE, and then we have a free spot right here. To show where like an example of where it's, to go back to just where we see kind of what might look like a garbage location, or it might just be the last latched address. Let's just zoom in at some point here in the cycle, and we'll find that empty spot again. So 2 reads from this E region again. So this is our full 2 word sprite read. 2 words of tile data, 1 word of sprite read right here from E2F, and there's just this region right here. If there was a read or write pending from the CPU, this is the place where that would happen. So we just kind of have garbage addresses coming out from some kind of probably uninitialized registers inside of the GA25. But it will, if there was a write or read pending, then these would be the addresses, and we would have the write enable flags and the output enable flags toggled to read that data. So that is a little deep dive into, so like, how is this useful? You know, I can now kind of understand how the GA25 is arbitrating access to this VRAM memory. Like it is cycling through like a kind of state machine loop of several different modes. There's like a start of line mode where it needs to read the offset information, and then there is the rest of line mode where it's reading tile maps and sprites together with a 1 or 2 cycle interval that can be used for CPU reading and writing into that memory. I've always kind of been surprised that they don't, mostly all the ARM hardware I've looked at has had a pattern pretty similar to this. I'm always surprised that here during the sync or during the VBlank, they don't allow kind of unfettered access to reading and writing VRAM. Like at this point here, nothing's being displayed on screen. The sprite processing doesn't even run. The tile map stuff doesn't need to run. Like you could give the CPU just full access to write as much data as quickly as possible as it could into VRAM at this point in time, but they always just kind of maintain the same simple state machine that exists whether or not it needs to be reading and writing from VRAM. So I hope that's been kind of informative. it's been informative for me, for sure. But that is one of the reasons I like to set up these test cases, because I can see very clearly what's being read and what's being written, and I can control it. So like the next thing I would do here is try to find where we are kind of where the top of the screen here is reading these white pixels, but to do that I would need so to actually see what the data values are that are coming out of that. That will allow me to understand like how much time does it spend between the start of a frame or the start of a line and before it actually starts displaying information.